Hello, everyone, and thank you for attending today's webinar. I am Deborah Walston, and I will be today's webinar moderator. Before we begin, I'd like to review some housekeeping items. The audio is muted except for our presenter. If you have questions or comments, please use the Q&A feature to submit them. We will address your questions at the end of the presentation. To open the Q&A feature, scroll your mouse to the bottom of your screen and click on the Q&A item. We're recording today's webinar, and we'll post a presentation and recorded webinar in the SPE library. You also receive an email with a link. We are thrilled to have Olivier Catherine here today to discuss capillary rheometry, application to extrusion. Olivier has 20 years of experience in the plastics industry as an expert in polymer processing, polymer rheology, and process modeling. He graduated from CEMEF Paris Tech in France with a Master's of Science in Material Science in 2001. Since his graduation, his interest in material science led him to a position as a project engineer on the development of PVC window profile extrusion dies and as a research engineer in the development of new processes and products for groups involved with rheology, polymer characterization, numerical simulation, and polymer processing. In 2010, he joined Cloeren Incorporated, a solution supplier for co-extruded flat film, sheet, and extrusion coating tooling technology. As a corporate scientist, he is responsible for technology advancements and implements new rheological tools and flow simulation capabilities. He works on die design with Peter Cloeren, developing new concepts like the patented Mobius manifold. He is a member of SPE, the Society of Rheology, PPS, and TAPI. He is a past chair of SPE's extrusion division. Let's give a big welcome to Olivier Catherine.
Well, Deb, thank you very much for the kind introduction, and thank you everyone for attending this webinar. This in 2021 is becoming sort of the new way to interact and present other than past conferences. I would like to also thank Netch and my friend Eric Bennett, who gave me this opportunity to present this presentation today on capillary rheometry. As you know, or you may know, Netch recently acquired the Rheology business of Malvern Panalytical. And also a big thank to SPE for organizing this webinar, of course. So yes, today I will talk about applied rheology and how do we use capillary rheometry for process and troubleshooting and equipment design in extrusion. So my company, Chlorine, we are a manufacturer of flat film, sheet, and extrusion coating equipment, and specifically the tooling part of the process, which includes co-extrusion feed blocks and co-extrusion dies. You can see here a picture of a complex system that is used for cast polypropylene, for example, made of a feed block up here and the wide die up there. Here's another picture of actual system running that was presented at K-Show in 2019, and is our newest technology called the Reflex Die, which is a high-performance cast film extrusion die. Here in the application, a cast stretch film running again at K-Show. So many applications are coming from our products. For example, cast stretch film, as I mentioned, is a big application for us. But there are many, many other applications where cast film and sheet is used by our customer, produced by our equipment. For example, here's a PVB interlayer that's used for lamination of glass panels for windshields. Medical applications such as blood bags, a lot of flexible food application, as well as other food applications such as milk cartons and rigid packaging. So why is rheology important for extrusion? When we design dies, we are really trying to optimize many things. And for example, the main goals are really to design a die flow channel that will deliver a uniform flow distribution. Also, the pressure drop through the system needs to be adapted to the process and the material. And finally, a residence time also needs to match what the polymer can tolerate for this application. So if you look at a simplified system, simplified equations to calculate pressure drop through such a system, which is made of a manifold, which we can simplify into a pipe flow, the pressure drop is directly related to the output or the flow rate through the viscosity parameter. In parallel plates, such as the pre-land or the lip land, you can also link the pressure drop through those sections of the die to the flow rate locally through polymer viscosity. These equations are simplified for Newtonian fluids, and in most cases, polymers are not. And also, viscosity is shear dependent or shear rate dependent and also temperature dependent. But the point is that viscosity is critical to size and optimize the system to reach the three goals that we just described. As I said, polymeric materials are non-Newtonian materials due to the fact that they are micromolecules. And as you're gradually shearing these macromolecules, you're basically starting to disentangle the macromolecular structure. And when you do that, the structure will tend to recoil. And there's basically a competition between how fast we are disentangling the system due to shearing the material and how fast it can recoil. And this is the shear thinning effect. And you can see the viscosity is initially at low shear rates, Newtonian, then starts to shear thin. Eventually, we are shearing the material so fast that everything is disentangled, and we are reaching another theoretical plateau at low viscosity and high shear rate. For polymer melts, though, we rarely see that plateau because we are in a shear rate region that's more covering the Newtonian plateau, the transition region, and the shear thinning region there. So what are the typical measurement techniques available in our market? Well, the first technique that's very widely used is the melt flow index. But I'd say that this technique, even though it's a standard, has very low value to us. The way it works is as shown here. It kind of looks like the COVID vaccine a little bit, huh? But so you are melting a polymer and pushing it with a standard weight, collecting the material coming out for a time of 10 minutes and measuring that weight. And so you have a pretty meaningless unit of grams of polymer per 10 minutes with this size of weight that you used at a given temperature. So it's very hard to translate that number into something meaningful to design or troubleshoot any process. However, it's an industry standard, and it's a simple way to quickly compare different polymers and or within the same family, let's say, and or also to do some QC, for example. Although I think there's different ways or better ways to do that. This is an illustration to show that you could, in fact, be dealing with very different polymers with very different flow behavior and still have the same melt flow index value of 5 grams, for example, per 10 minutes. And you can see here that I'm representing a polymer that shear thins a lot less in red compared to the blue polymer, which starts off with a much higher zero shear viscosity in this case. If you were to design equipment the same way for the blue and red polymer, you would end up probably in some trouble at some point. So other technique that we, for example, use in our lab here, rotational and dynamic measurements. And the main reason is that this technique can bring a wealth of information regarding viscoelastic behavior of the material. So there's different ways to perform measurements, but here I'm showing sort of a typical setup where we use either a cone and plate or a parallel plate geometry, and we use the equipment in small amplitude oscillatory shear experiments. So basically we are shearing at a frequency the material, and we're gonna vary that frequency. So this is here a representation of the strain and response in shear stress for the material. And the main thing is that as we impose the strain, we are going to see a delay, a shift in time for the response in shear stress, which is shown with this delta value. And from there, we can derive many viscoelastic parameters that are quite interesting. So for example, the modulus that we are measuring during this, which derived from the torque measurement, is composed of a real part and an imaginary part from the complex modulus, and where the real part is linked to the elastic behavior of the material, and the imaginary part is linked to the viscous behavior of the material. So here on this scale, I represented sort of a typical behavior from liquids to solids, and they have a sort of a gradual increase in elasticity. And polymer melts are really a true viscoelastic material, so meaning that both elastic and viscous components are important, and that importance is actually going to vary as the frequency is changing. So for example, I've plotted here a study that I've run some years ago to characterize the viscoelastic behavior of extrusion coating grade polyethylenes. So on the left here, the blue material is LDP1, which is a 7 melt flow index material with a density of 0.917. And as you can see, it's a very standard extrusion coating grade material, and I will use it as a reference and compare that to other extrusion coating candidates. So what we are representing here is the different components of the complex modulus. So the G double prime, which is the more viscous component of the modulus, and the G prime is the elastic component of the modulus. And you can see as the frequency increasing, the elastic component is getting closer and closer to the viscous component. And eventually we have a crossover and the material becomes elastic dominant. So this crossover point is a very interesting characteristic of the viscoelastic behavior. And I have here another LDPE, which I call LDPE2 for a very original naming here, which is a very similar material on paper. It's also a LDPE with a melt index of 7 and a density similar to the reference material. And as you can see, I mean, the crossover point between G double prime and G prime is very similar in frequency compared to our reference material. But I can see a little bit of a difference here. My G prime seems to be more close to G double prime. So it seems like in the terminal region, the material's melt elasticity seems a little higher than that of the reference material. Now, I picked a more drastic, different material here, which is also a candidate for extrusion coating. It's a trend of using more and more a metallocene grade. And the metallocene molecular structure is much more linear and also much more organized compared to this autoclave LDPE. And as a result, you see the viscoelastic behavior is quite different. We have a melt elasticity, sorry, which is very low in the terminal region. And we have a much greater delay in frequency for the crossover point. Actually, here we can barely see that crossover point on the range of frequency that we studied the material at. And then finally, just to show that sometimes melt index can have very low meaning. Here is a 16 mi LDPE. So even though the molecular structure is similar to that of LDPE1, it's a much more lower molecular weight material. And we do see a delay in the crossover point compared to the blue material. However, we can still see a substantial melt elasticity compared to the blue material. So overall, this material, even though it's a much more lower molecular weight and higher MI value, we can see very similar viscoelastic pattern between the two. So now if I compare the complex viscosities, you can see that my reference material in blue here, we did see a little bit more melt elasticity for LDPE2, and you can see that that translates into potentially a slightly higher zero shear viscosity. And but though the at high frequency, we have a very good match in shear thinning. LDPE3, which is the material that did show very similar viscoelastic behavior with a slightly delayed crossover point, shows very similar shear thinning at high shear rate or high frequency. But compared to LDPE1 and LDPE2, we see a lower zero shear viscosity, which is understandable and also matches the 16 mi value versus 7. And finally, MPE, the metallocene grade here, shows a very Newtonian behavior and very much in line with the low melt elasticity. And then eventually we see parallel shear thinning behaviors at high frequency. All right, I will really talk about capillary rheometry very soon, but that's trying to cover all the different techniques here. One nice feature also about these type of rheometers is you can change the instruments or the measuring devices and have access to a lot more information. And also you can explore the molecular structure of your materials. For example, here, a tool I really like is that being able to measure transient extensional rheology. And the way it works, we basically use a piece of film of a given sample and melt it in a convection oven, and then we start stretching it with those rotating drums. I have here a little movie. Unfortunately, my camera, which I really liked, got flooded during one of our hurricanes here in Texas, and so I lost that camera and that capability. But you can see, it was really cool. We could see what's going on in the oven there, and once the polymer is melted, we started stretching it and measuring torque. As we do that, we are able to convert those values into a transient viscosity over time, and compare that to the Troughton ratio, which is basically the shear viscosity multiplied by 3. We are able to detect or compare behaviors of materials in extensional mode. So for example, here our LDPE1, which is a very highly branched molecular structure, you can see that the transient viscosity is at different strain rates is departing very quickly from the LVE, which is a linear viscoelastic envelope, which is basically a Troughton ratio I was mentioning. So the shear viscosity multiplied by 3. And so this is similar to a strain hardening behavior in tensile test, and really shows the melt strength of the material or the lack thereof. As you can see here, the metallocene grade, very linear molecular structure, did well. The measurements were actually quite difficult, but you can see that there's no strain hardening at all at any strain rate. So these tools are really great to compare viscoelastic behaviors and investigate the molecular structures and relate that to also processing. All right, capillary rheometry, which is really the topic of today. I put here a picture of the new niche RH 2000 and 2200, which is basically a dual bore version. And this is the rheometer we use in our lab, and a great rheometer to complement all the techniques. We use this rheometer all the time as well. I mean, we use both our rheometers all the time, but this is a very busy piece of equipment. Here's an illustration of melt fracture. Is one nice feature you can detect or observe in the rheometer. So the principle is similar to that of the melt index, except that this now is instrumented. So principle is that we load the polymer pellets in a barrel, in a heated barrel. The temperature of the barrel is controlled very precisely through a very precise controlling system and precise measurement system, thermocouple embedded in the deep in the metal of the barrel. Once the polymer is melted, we push it, but the main difference is that compared to the melt flow index is that we're not using a weight there, a dead weight. We are using a controlled speed system, so we are able to control the speed very, very precisely. And through that, we control the flow rate, and the polymer is now flowing through a capillary die. So this is a little too small, so if you move on the right side here, you have a blown up version of this picture. The capillary die is a very precise channel of known dimensions, namely the length and the capillary diameter. And from these features, we can calculate shear rate. As we are doing this, as we're pushing the material at a control speed, we are measuring the pressure that is resulting from this flow. And the pressure is measured through that membrane type pressure sensor. And from the pressure, we are able to calculate the shear stress. And the viscosity is basically shear stress divided by the shear rate. So this is fairly simple in theory. However, there are some corrections necessary to get to the most precise, most meaningful measurement. The first correction is the so-called Rabinowitsch correction. So when we calculate shear stress, we actually apply, again, simplified equations that assume the material as being Newtonian. And the equation only uses the flow rate of the material and the radius of the capillary or the diameter of the capillary. But as we are dealing with non-Newtonian materials, the velocity profiles are changing as the material is flowing through the capillary, as shown in this graph here. So a fully Newtonian material would be that dark purple color. And as the material are actually more like shear thinning materials, you can see that as they become more pseudoplastic or less Newtonian, the velocity profile tends to flatten, and eventually, even for a completely a pseudoplastic index of 0, you have this black line here. Now, shear rate is the slope of this velocity profile at the wall. So as you can see, the shear rate is affected by how non-Newtonian the material is. And shear rate increases, the slope is increasing as the material becomes more and more pseudoplastic or less Newtonian. And that's the correction proposed by Rabinowitsch here, which uses the n value, which is a local pseudoplastic index. And physically, how do you, or practically, how do you do that? You basically calculate the n value with a polynomial fit of the log of the wall shear stress as a function of the log of the apparent shear rate. You fit this and you're able to determine the n value. And of course, there's different ways to fit that. You can do linear fits or a more higher degree polynomial fit. So this is what I'm showing here. We have data that we measured with our system, and in blue is the data for the shear rate, which would not be corrected. So no Rabinowitsch correction here is shown. And then in red, we have, well, sorry, in green, we have the linear correction of the Rabinowitsch. So basically a degree 1 polynomial function. And then in red and orange, we have quadratic and cubic, so a degree 2 and 3 polynomial function, which I think gives the best correction in the end. So as I was explaining on the graph of the velocity profile, using a correction ends up shifting the data to higher shear rates. And that's what you see here. The second correction is a so-called Bagley correction, and is explained by the fact that the pressure sensor is physically limited to a location upstream from the capillary die. Of course, when we want to calculate the shear stress at the wall of the die, we would need to use the pressure drop through the die. However, the measured pressure, because of the location of the sensor, is a combination of different features. And this graph shows here the different features. So we have, in this region, we have an entrance pressure, which is very strongly dependent on how elastic the melt is. Okay, this can be a small value or it can be a great value. Then we have the capillary pressure, which is mostly driven by the shear flow and a little bit of elongational flow as well. And finally, we have an exit pressure, which because of the swell and the also the elasticity of the melt can be non-zero. But you know, in general, this pressure is fairly low. So the the Bagley correction consists in trying to determine this entrance pressure by changing the L over D ratio of the die. So that's the historic Rabinowitsch correction. I'm sorry, Bagley correction. And so basically you would plot the pressure measurement as a function of different L over D ratio. So you would have to use 3-4 different dies, repeat the measurements, and collect pressure as a function of this L over D for different shear rates. In the end, you can calculate, at the intercept here, you can calculate the entrance pressure, or with the slope here, you can directly calculate the corrected value of shear stress. This is something I've done a lot, especially when I was in college, and I can tell you it's a lot of work. Thankfully, and the Rheometer that Netsch is selling today, you have an option for dual bore, and this is a must because this dual bore option will give you the ability to measure pressure simultaneously on 2 different bores with 2 different dies with 2 different L over Ds. And specifically, they have L over D die close to zero. Here we call it orifice die or zero length die. It is in fact a 0.25 millimeter, if I remember. But basically with this on the right side of the rheometer, you are measuring the entrance pressure and you deduct or you remove it directly from the left side measurement, and you have a 2-point Bagley correction, which is very accurate and very, very efficient. So that's what we do all the time. You can see here again another example. Depending on the melt elasticity of the polymer, this may or may not be as big as this one. In this case, I would say it's a moderate correction. I have seen melts that being much more elastic where the uncorrected value was much, much higher than the corrected value. Again, keep in mind that because you're removing an entrance pressure, your corrected pressure will result in a slightly lower viscosity compared to uncorrected. In some cases, this can have a huge impact on how you design your extrusion equipment, because at high shear rate, you could have some pressure estimation that are wrong if you're not applying the correct corrections. The rheometers can, like I say, bring a lot of very interesting information for die designers. One example I wanted to discuss today is flow instability and melt fracture. And for example, we designed a lot of dies for fluoropolymer applications. So here are some examples of fluoropolymers like FEP and PFA. So highly fluorinated molecular structures and very specific flow behavior. These materials tend to very quickly become unstable in the flow. And you can see here examples of a development of melt fracture as that's the strand that we collect out of the rheometer. As you can see, we are going from, in this case, a surface type melt fracture to a more volume like melt fracture. So it's nice to observe that, but actually being able to measure this phenomenon is also quite good. So here's an example of pressure measurements from the capillary rheometer for a fluoropolymer, and this is over time. So we impose different shear rates. So we schedule those shear rates through the software of the rheometer, and as a result, we are measuring the pressures. And as you can see, we start in this experiment, we start from high shear rate to low shear rate, right? And you can see that we are, at the very beginning, we developed a very unstable flow. We have a lot of pressure fluctuation. And eventually, pressure stabilizes to, in a steady region there, we are able to collect an actual pressure value. And from there, we can convert that to shear stress and later viscosity. If you plot the resulting viscosity as a function of shear rate, we can clearly see a Newtonian behavior, and eventually those materials become very unstable. The flow becomes very unstable, and we have a very extreme shear thinning, which is actually a fake shear thinning. It's actually linked to slippage. We have some slippage going on. If you calculate the pseudoplastic index there, it will be 0, which means that it doesn't have any physical meaning for the material. It's only slipping there. It's a very unstable flow. But we are able to detect with both graphs here, we can see the transition from unstable flow to stable flow. In literature, that's called a critical value of shear rate or shear stress, depending on how you see things here. So I wanted to show an example of actual example of a customer who was extruding PFA with a competitor's die, and we're having some flow instability at the edges. And this customer is actually making a sheet and has a fairly large lip gap. So when I measured the PFA, I found that the shear rates at which the flow became unstable was extremely low, right? So we had a very narrow processing window with those materials. But indeed, the sheet die that they use has a huge gap. So I wouldn't expect the shear stresses or the shear rates to be high in the lip land region. So I ran some flow simulation with the material flow behavior I just determined. And for some reason, this die was trying to push more material at the edges. And you can see that the velocity, the computed velocity was quite high in the pre-land region there, near the edges. When I looked at a map of shear stress calculated from a flow simulation, I found that the shear stress was higher than the critical value in the pre-land region. So not at the die lips, but upstream. And so I think what's going on is that we are starting to see some flow instability in the die flow channel, and this flow instability will not dampen or will actually continue to be unstable as the material is flowing out of the die. And that's exactly what they saw at the edges of the sheet there. Another great feature of the Rheometer is being able to observe how stable materials are. And sometimes it's a fight because we have material that tends to degrade before we're done with our viscosity measurements. But I can also use the Rheometer as a device to determine if the material is stable or not. So here's an example of another fluoropolymer, a partial fluoropolymer and a chlorinated fluoropolymer, so ECTFE. This ECTFE material, in fact, is quite stable thermally. So what we do is we measure pressure of a capillary flow over time for a long period of time, and we do basically some kind of time sweep. And if the material is stable, the pressure remains stable. So we did this at two different temperatures for the neat polymer, and everything is fine. And so we actually designed a die for this neat polymer, but then the customer was trying to extrude the material with additives and never told us, right? So the die was performing fine with the neat polymer, but then they were observing a lot of degrading materials very quickly when they were using additives. I still don't know today what the additive is. I can tell you that after the fact, we did the same time sweep experiments, measuring pressure over time, and the additive had seemingly a strong effect on pressure, and we could see that the material is starting to degrade at 270 degrees C, and at 290, the degradation was dramatic. Of course, so you can do these type of measurements, but also in everyday life, you can also just observe the material and how it comes out of the rheometer. This is here examples of flexible PVC, which is also a material that's very thermally sensitive and tends to degrade. So you can see some discoloration and some strong burning effect eventually. So things are nice, and you can determine how long the material is stable for. And how does that apply to my extrusion design? Well, I can tell you that this is very valuable piece of information compared to the residence time in the extrusion process. So here's an example of flow simulation that's using particle tracing to actually determine residence time in an extrusion die. I just wanted to show you this die is upside down for some reason. Okay, this is the entrance, this is the outlet, and I just wanted to illustrate the fact that when you talk about residence time, it's not just a simple number, but you're really dealing with a distribution of residence time. And you can see here, actually, based from these flow simulations and particle tracing analysis. This is the envelope of residence time as a function of the position and width of the die. So particles coming out from the center line at 0 to the ends of the die at over 1,000 millimeter for this one application. You can see the envelope is this type of asymptotic behavior. And therefore, when we talk about a residence time, I'm always curious what people have in mind, but usually it's a much more complex notion than just a 2-minute residence time and so on and so forth. The other thing I want to also point out is that when you look at a die and you have degraded material coming out, the die is the last piece of the hot portion of the system, of the extrusion system. You really have to consider the whole line's residence time. So residence time in the extruder, in the melt pipes, in the screen changers, melt pumps, and so on and so forth. Whatever is in between where the pellet is dropped into the extruder to the die lips, all this is a complex system with a complex residence time distribution. So while it's nice to have information on how fast the material degrades from rheology, it's also hard sometimes to directly apply it to the system, or at least we have to keep in mind that the system is complex and it's just not a 5-minute residence time. However, then you can use this method to compare if one material is stable through the system and then you have another that's not. You can determine, comparing from the rheology lab to the process, you can apply and troubleshoot. Let me see how much time I have left. This presentation I just finished last night, basically, so that's pretty usual for me. But it seems like we have about maybe 8 more minutes. I wanted to discuss really quickly about a troubleshooting example, a specific troubleshooting example of PVB film that I've done in the past, and I thought it was quite interesting, because this is a real-life extrusion application. We designed a die for a specific process, and the die was installed in Asia, so far away from here, and this was on an existing line, and we had some very different results with the die, or let's say the system, than we were anticipating. So this is PVB, it's polyvinyl butyl, and we measured this material quite well with our capillary rheometer in the lab at 3 different temperatures. You can see very nice measurements. We are able to fit the data quite well with a classic cross model using a WLF temperature dependency. Here are all the parameters. You can see the curve fit is quite nice, right? From that, we design a die based on not only the viscosity measurements, but also the process information given by the customer. So the die will be set at 210, the melt temperature will be set at 210 C, extrusion output is 800 kilos per hour, and we design the die, optimize the flow channel, like as mentioned, with the 3 main parameters, which are uniform flow distribution, a pressure drop, which makes sense. In this case, we're targeting 10 megapascal or 100 bars. And of course, we want a residence time that makes sense with the temperature, with the material sensitivity. These materials seem to be fairly good, actually. Here's the result. So we have a pressure drop of 12.5 megapascal, which is very nice, and a very, very uniform velocity at the die lips, computed from commercial 3D computational fluid dynamics. Same results showing here, actually a plot of the velocity distribution at the die lips. And you can see, compared to the theoretical design, we have a flow variation of 1.3%, which is basically nothing. However, in real life, when we started this die, we observed this phenomenon. We observed without doing any lip adjustment. So we gapped the die at the uniform die gap. And you can see that the resulting gauge measurement online was crazy. I mean, we have very heavy end flow and very poor center flow. So the material is all flowing at the edges, basically. This is characterized with a gauging system with flow variation of 2 sigma, heavy end flow of about 17%. Now, the die still works well because once we turn on the automatic lip adjustment, we end up with a flat film, which is good. However, to go from here to there is some time, and we waste some material and we waste some time. But more importantly, we were not expecting this type of behavior. This is here an illustration of the lip adjustment system and the automatic. This is a thermal system that's based on a feedback loop from the online gauge measurement, and the die will be adjusted every inch. We can adjust the gap of the lip. So what did we do from there? Well, we suspected that the material melt temperature was not what they were specifying. So we use 2 techniques to characterize that. One is actually to use the melt temperature in the flow itself, and also to measure the melt temperature in the air gap. So was the material coming out of the die with IR imaging. And finally, we wanted to make sure that the material that they were actually extruding that day was the same as the one that we designed the die for. So this is a simplified layout of this PVB process. It's a twin screw extrusion using a gear pump, static mixer. So it's a quite complex system, let's say. Then there is a adapter, and then the die, and the material is coming out into a water bath. So we measured the melt temperature as close as possible from the die entrance, and we used, so there's an elbow there, and that's what we used. There was a port we could use, and we used a variable depth thermocouple. So this device is very useful for extrusion troubleshooting. We can measure the melt temperature in the melt at different locations. And we can plot this profile. So from the wall of the melt pipe or the adapter here, all the way to the center of the flow. Once we're done with the measurement, we recommend strongly to retract the probe. Otherwise, it can get broken during startups or shutdowns or wrong manipulation. But the cool thing is that we were able to determine that the melt temperature was higher than what they specified at 210. So 210 was really the target, but due to some poor control of melt temperature, this customer was basically trying to cool the melt in the melt pipe by setting this temperature set point at much lower, so 180 C. So that's why you see initially near the wall 180 C, and then at the center of the pipe a much higher melt temperature than specified. This was also confirmed with thermal imaging, but the cool part of thermal imaging is that you can also look at that response as a function of extrusion output, and you can see here there's almost a linear temperature increase as the extrusion output is increased. So it really shows that there's quite a bit of shear heating in the system, which is not unusual for these high viscosity polymers. Lastly, I was there at startup and picked up some material and remeasured this material in my rheometer. Instead of 3 temperatures, I did a 4 temperature characterization and apply, again, the cross model. And what was interesting, that PVB is actually a plasticized material, and coming from the twin screw extruder, I believe that there is some influence on how that plasticizer being distributed or mixed can have on the flow behavior. The original material, I still don't know exactly how it was made, but the startup material was coming directly from the line and was really a true characteristic of the extrusion process there. Even though it was the same formulation according to the customer, it seems like the process did change something. So the new material that we characterized showed some lower zero shear viscosity and also, quite interestingly, higher shear thinning effect. So when I took into account all these changes, higher melt temperature and change in the viscosity behavior, well, first I found a lower melt pressure compared to the 12.5. We predicted 10.4 megapascal, so it's about 20% reduction in the melt pressure. And regarding velocity, I can see also a trend, which is a much higher end flow. So if I plot this velocity profile at the die exit, I can definitely see the combined effect of higher melt temperature and new viscosity behavior, and see that there is definitely a resulting push towards the edges. And the actual 2 sigma calculation for this profile is about 15%. It's not that far from what they observed at 17%. So I was quite excited to see a good match like that. So from there, we have a good, solid data point, and we can go back and correct the die flow channel for their process, or see if there's any adjustment they can do on their extrusion process to minimize the shear heating and also avoid that temperature mismatch that they were trying to cool the melt from. So in conclusions, I think I've shown today that rheology and flow characterization of polymer melts is a very important piece of extrusion equipment design and troubleshooting. Capillary and rotational and oscillatory rheometers have both their own advantages. However, capillary plays a really important point and provides a wealth of relevant information, especially for melt fracture, thermal stability, and direct viscosity measurement. There are some necessary, and I would say mandatory corrections that need to be done to get the most precise measurement, but that can be done. Finally, I think a combination of rheology and flow simulation is a strong, powerful tool for design and troubleshooting. We've been using this for years now. One point I want to make is that data interpretation is as important as the accuracy of the data itself. So for example, when we measure flow of polymers and we see that very strong shear thinning, we have to understand where that shear thinning is from. When we're dealing with, for example, highly loaded melts, like very highly loaded, like almost like polymeric slurries or materials with very high concentration of solids, we can have some very strange flow behavior at low shear. That we also need to understand that, the way you interpret the data and how you model this data is quite critical, actually. And with that, I think we may have a little bit of time for questions, and I will actually be able to stick around for a longer than planned. So please feel free to ask any question. And thank you very much for your attention. Thank you, SPE, and thank you, Netch, for giving me the opportunity to talk today. I hope I didn't talk too fast or too much. I think I did, but I hope you enjoyed it as much as I did. Thank you.
Thank you, Olivier. Let's take some questions from the Q&A window. The first question, is it possible to process the melt at such high shear rate that it will completely lose its memory and will be purely viscous material, even when the acting shear stress is removed?
I'm not quite sure I fully understand the question. So maybe what I could do is that what I propose is that maybe Deborah, you could send that question to me, and I have to think about it and then answer that, because I think there are a few contradictions in that question. The memory effect is linked to the elasticity, right? So material that has high viscosity will also end up with a lot of could end up with a lot of melt elasticity and a very strong memory effect. So I'm not sure I quite capture the question. So
Sure.
maybe.
Yeah, it was submitted anonymously. So whoever submitted it, if you want to either contact Olivier with his contact information there, or if you want to resubmit your question with more clarification, that would be fine.
Yes, thank you.
Next, why does polymeric material with similar or same melt flow have different shear viscosities?
Sorry, say again.
Why does polymeric material with similar or same melt flow have different shear viscosities?
Okay, so if you have material that have the same melt flow and similar shear viscosities, they would probably be of the same molecular weight distribution and molecular structure. So basically, the shear thinning effect is really depending on how broad the molecular weight distribution is and how what's the construction of the macromolecule, so the structure. So if you are matching both the viscosity curves and the MFI value, you're basically dealing with this same two features. So
Okay.
similar families and similar molecular weight distribution.
Next question, is it possible to identify and quantify long chain branching in polyethylene by rheology techniques?
Yes, so what I was showing as far as so there's different ways to use viscoelastic data, different plots that can be done. They're quite interesting, but one way is to be sure is to combine the shear rheology with extensional rheology, and extensional rheology with the way the extensional viscosity is actually departing from the LV curve. That strain hardening that I was mentioning at the very beginning of the presentation is really a characteristic of the long chain branching. Because if you are looking at only shear data, you can have the same sort of effect from the very high zero shear viscosity could be coming from either a very broad molecular weight or coming from the branching itself. So it's really hard to distinguish from the shear rheology only. And that's why you have to move to another type of strain. So extensional will definitely, in combination with the shear, will definitely tell you the presence of long chain branching and how much impact it has on the elongational viscosity.
Okay, next question. Does the sequence of applying Rabinowitsch and Bagley correction matter?
Well, typically, not really actually. So it doesn't matter. The thing is, when you do the Bagley correction, you usually use the apparent shear rate. So if you follow the procedure, it should not matter.
Okay, next. Now, this is a long question. Have you looked at generating apparent viscosity data with an instrumented nozzle on an injection molding machine?
Not currently here, but I have looked at that in a previous life. So when I was actually at Saint-Gobain, we had access to very nice injection molding machines. And we were looking at building, at some point we were looking at building a rheometer, a slit die rheometer that way. The same concept can be actually applied to extrusion and on online type rheometer on an extruder. There are limitations of that method. One, for example, in injection molding, to know the exact flow rate of the material you actually it can be quite difficult because most people actually assume injection speed and convert the injection speed into a flow rate, but there might be some leakage through the check ring, right? So that we don't know exactly those values. So there's quite a bit of uncertainty there. For extrusion, it's the same thing. The output can be actually measured by just collecting material over time. Or you can use a gear pump for that, and you have a better control of the flow rate. But both methods are very interesting. Although another limitation I want to say is that at high rates, you can have quite a bit of viscous dissipation also. So the melt temperature can be a little bit off. So those are things to keep in mind. However, what I like about those techniques is that you're really measuring in situ, so you're really characterizing the melt that's being processed by a given extruder or a given injection molding machine, and that has some value there for sure.
Okay, and it continues on here. With pressure transducers in the nozzle away from the ends of the stream, Bagley and Rabinowitsch corrections can be eliminated. In addition, the melt is prepared with a shear history experienced in production processing, unlike just conduction, zero shear in the lab equipment. One can also characterize highly filled materials not easily run in a standard LCR. What are your thoughts?
Yeah, so there's different ways to go around the Bagley correction. For example, also using a slit die, you can instrument a slit die at different lengths of the slit with several pressure transducers and determine the pressure drop through the slit directly and avoid that entrance effect, basically. Additionally, you can have a little more precision on that exit pressure, and you can that can be linked to some other viscoelastic features that quite interesting. So that was for the Bagley one. Sorry, I forgot the second part of the question. Would you mind repeating?
Yeah. In addition, the melt is prepared with shear history experienced in production processing,
Yes.
unlike just conduction, zero shear, and lab equipment.
Yes. So there are materials out there where basically one limitation of the rheometers is we are really melting with conduction, and we're not really melting with what's happening in the process, which is a combination of a little bit of conduction, but mostly shearing the material. And some materials like, for example, PVC are really melted. They are really actually almost not melted, but they're prepared by shearing, right? And this shearing has a huge impact on the flow behavior. Just melting the material through heat conduction is not as good in this particular case, right? So actually some people have developed really strange rheometers with a pre-shearing unit. And there are some quite interesting ideas out there for sure. Yes.
Okay. What software was used in your simulation?
So I use a generic commercial software. In this case, what we've done is it's a CFD software that's attached to SolidWorks, and it's called Flow Simulation. It's a very interesting name. So Flow Simulation has a capability for non-Newtonian materials, and the cross model that I showed was is implemented in there. And then we can also implement some more sophisticated flow behaviors as well.
Okay, next. When you perform the time sweep on thermal stability, is it based on the capillary rheometer?
What I showed today, yes, it was showing pressure. So pressure as the material is flowing through the capillary die, and for a long time. So we basically do at a fairly slow speed. But of course, you can apply the same thing to a rotational experiment. So these, the time sweeps can be applied to both rheometers.
Okay. Will Olivier cover co-extrusions, example, COPP, HOPP, COPP?
Next time, maybe? Yes, I had actually some quite interesting things I wanted to show on co-extrusion. the effect of shear thinning and how polymers in different layers can fight through viscous forces, is what I like to say. There's quite a bit of interesting things, and it's quite complex.
Okay. Is it possible to simulate the die flow of polymer filler oil type additive as well?
If you're able to characterize the flow behavior, yes, some of the flow behaviors there can be quite complex. So it can involve some wall slippage, it can involve some yield stress at low shear. So if you're able to characterize that and model that, then yes. That's what I meant by the interpretation of the data. Just looking at viscosity versus shear rate and applying these to a model will not do good if you don't understand what's going on like that. So there's ways to determine slippage, which I haven't touched upon. I mean, there's so many applications with the rheometers. But for example, there's a so-called Mooney method, which is using dies with increasing diameters with a similar L over D. And you can do shear stress measurements and determine slip velocity from that if you estimate that there is some slippage. And then that slip velocity is a function of shear stress can be implemented in your model. So yes, a lot of things can be done.
Next question. You mentioned that cubic are better than quadratic fit to viscosity data, but how important is this difference?
No, what I meant is quadratic and cubic there give me a similar or acceptable result, which I was trying to compare with the linear, which was not acceptable. I didn't really explain very well there. So maybe let's jump back to that real quick. I don't know if we have time. Okay, so if you look at the uncorrected data and you look at the linear data, I did not like the linear data in this particular case because so if you look at the data with the quadratic and the cubic, I think they are quite similar. Well, the quadratic seems to be stretched a little more. The shear rates are corrected more than the cubic in this case. But what I like though is that low shear, where the material becomes more Newtonian, locally the pseudoplastic index should be getting close to 1, and your Rabinowitsch correction should be almost none. And so these two corrections make sense because the blue material, the blue measurements and uncorrected and the corrected sort of makes sense here. At the low shear rates, the linear was correcting too much, I think. Because of that, what I just meant is that when you're close to the Newtonian plateau, you should not have any correction. In the Newtonian plateau, you should have a zero correction. And this is what you are seeing with the two quadratic and cubic. Now, I didn't really comment between quadratic and cubic. In theory, cubic is better because you have a little more freedom to fit the data. However, if your data is a little noisy, it can amplify and create some error. So that's why you have to choose between the two. You got to compare and see what makes sense. But most likely, I would never use that linear. Practically, that's what I found, right? But then I would spend maybe some time in looking at quadratic versus cubic.
Okay. Can you please comment on the degradation experiment and thermal stability with additive in regards to molecular structure? Just curious why the pressure increases.
Yes, that's a good point. We see degradation going both ways. So what I mean here is that in general, the viscosity is changing or the pressure is changing over time. In this particular case, I don't know what the additives was, but what the result is seems like it did increase the viscosity quite a bit, and basically material was burning, right? Almost like this picture here. You can see cross-linking doing similar trend, but sometimes we also see degradation where the material molecular weight is going down and the viscosity is going down as a result. So for example, if you are looking at PET and you have a little bit of moisture, over time you will see a decrease in viscosity. So it depends. In this particular case, I did not know the chemistry of the additives.
Okay, next. How can the glass-filled nylon 66 polymer degradation be measured using capillary rheometer?
I would think similar than this is what's shown here. In nylon, I see usually also a trend of going up. So I see potentially some cross-linking over time. One thing is you have to be sure is that the materials are dried very well. Nylon is sensitive to moisture, so you need to make sure that it's dried properly before the measurement.
Next, nice example with non-uniform flow. It seems that the customer got high flow in the center and at the end. Did the simulation predict both deviations?
Now, the customer was definitely having too much flow at the edges. And what we were looking at is basically trying to explain why this was happening. And the explanation, even though it wasn't a complete proof, I mean, when we changed the parameters of higher melt temperature and the issue with the viscosity, the change in the material viscosity for some reason, then we were able to recreate their issue. And from there, the next step will be taken, which would be either trying to fix which I prefer is always to go back to their process and see what created the issue of melt temperature that is too high. And that's a very common problem in extrusion, is that the shear, the viscous heating or shear heating is usually much higher than people think. And then people try to correct that by having lower set points in the melt pipes and feed block in the die, and that really creates non-isothermal extrusion at this point, which is very difficult to balance. So it's always good to go back to the source and fixing the issue of the too high shear heating. So is it a screw design? Is it a melt pump that's undersized or something of that nature? And then hopefully get better extrusion.
Okay, next question. How different is the approximation when you process mixtures with calcium carbonate?
Well, calcium carbonate, it depends on the concentration. It will have some effect on viscosities in general. And if it's really highly loaded, you can see some strange phenomenon, such as some yield stress at low shear rate. So it really depends on concentration. And but usually what happens is high concentration of calcium carbonate will increase viscosity and change the slope of the, depending on what a carrier is, the slope of, so the shear thinning effect will be changed. And also don't keep in mind that the density would be changed and the thermal conductivity. So when you are looking at the thermal aspect of the flow, this can have an impact as well.
Okay. In the flow curves you presented with the unrealistic shear thinning, how much could the slope be corrected reliably using the Mooney correction?
Well, I cannot touch upon that. The Mooney correction will give us a slip velocity that can be implied in the model. The point, though, in this case was that that's a region of the flow we're trying to avoid altogether. The flow is becoming unstable. And so for good extrusion, we don't want to even be there. So whenever you see shear stresses that are higher than the critical shear stress, yes, the result can be, the model can be, if you don't take into account any slippage, the model can be wrong, but that's not an area you want to be in the first place. So you really want to be in that Newtonian flow and trying to understand, if the shear stress values are really below that critical shear stress. That was the goal there.
Next, what is a good target for maximum die lip variation percentage?
Maximum die lip variation percentage. I don't understand that question. Sorry.
Okay, whoever submitted it, if you want to maybe clarify and resubmit.
Maximum die lip. Yeah, I'm not sure I understand.
That's fine. Is it relevant to measure capillary rheology on concentrates that are used at low letdown ratios, or should they always be compounded to understand the flow properties of the mixture?
That's a good question. Definitely prefer to have a compounded material where the master batch is dispersed in the melt. That way will characterize the flow behavior. The flow behavior of a highly concentrated master batch can be so different than it will not make sense or be representative of the flow behavior of the compound.
Next, from your experience, if you've worked with fiber impregnation before, how big can the impact of quasi-endless fiber / long fibers on the shear rates typically be?
Well, that's an area I'm not very familiar with, honestly. Fiber impregnation. So I would think that the flow and how it orients the fibers has a huge impact on the flow behavior, but I'm definitely not an expert there. Especially if you're dealing with long fibers. There is one time I had one material, a slurry. It's funny because in my lab I see a lot of different stuff coming in. And one time when materials show up in a bucket, I'm always a little worried. So this time it was a bucket of a slurry, and there seemed to be some fibrous material in there, and I was having a really hard time measuring the material. And I think the fibers were fairly long and almost longer than the diameter of my capillary, and basically it got clogged. So I didn't really like that one. I don't really have much experience with the long fibers, sorry.
Okay. Is there any way to calculate the swell using rheology information, especially when design profile die?
There is, I think so. It's also an area I'm not, I haven't really looked too much into details, but there's definitely a way to calculate through fully viscoelastic modeling, and that's quite intensive calculation. But like you would have to use much more complex viscoelastic models than what I've presented here, which were basically generalized Newtonian, so non-Newtonian material, but viscous only, basically.
Okay, next question. What is the best method to measure the viscosity of a two-component material in a capillary rheometer without pre-compounding? For example, glass-filled material added at some percentage.
I think the best way would be, if possible, to do some sort of in situ measurement from the extrusion where you compound the material, and with the same compounding machine, if you were able to online attach a Rheometer die and do the measurement there, that would be the best way. However, you could also compound the material with a specific machine that's representative of the extrusion process and collect this material sample and then process it or measure it in a capillary rheometer. That will work as well.
Next, how do you identify critical shear rate for a specific polymer?
Well, I thought I explained that. Basically looking at the pressure graphs as a function of time, and you could see the oscillation and characterize basically unstable flow. And then at some point the flow becomes stable, and this actually matches the extruded. So you see that type of melt fracture going on, and then at some point the flow becomes stable here, and the extruded becomes smooth. And the transition between the two is your critical shear rate or shear stress, and that's one method to do that.
Okay, next, how can a melt fracture be anticipated?
I don't think it can unless you are doing this type of experiment, and that's the whole point of. That's one big feature of the capillary rheometer, I think, compared to rotational rheometers, where you can physically see the melt fracture. You know, you can see the extruded coming out and melt fracturing like crazy. You can see stick and slip phenomenon. You can see when the flow is unstable. So that's to anticipate it. Just looking at the molecular structure or the MFI value, forget it. You have to run this characterization.
Next, is there something in the polymer design, for example, molecular weight distribution, viscoelastic behavior, branching, additives, that could help avoid the phenomena of dye buildup in a BOPP process?
Well, there's two things for dye buildup, and so I have to look at the BOPP process. The skin layers are usually a little bit lower MFR than the core layers, but they're still in the 7 to 8 range. The dye buildup is a complex phenomenon that can result from two different mechanisms. One can be almost what I call a distillation process, that we have additives that are more like volatiles and have a lower melt degradation point and starts degrading into a gas form and recondensate on the nose of the die. And little by little, you have an accumulation of gunk basically on the nose of the die. And that's one mechanism, right? It's what I call a distillation process. The lower molecular weight stuff is coming out as a volatile and then recondensates on the die. The second phenomenon is more micro melt fracture. So we have melt fracture that's coming from the skin layers, and little by little, a little bit of material detaches from the film and starts to accumulate on the nose of the die. Okay. So depending on which one of those two, what type of additives and strategy on your formulation can have, you can have different ways to deal with that. If you think you have a little bit of melt fracture, then definitely a PPA, a polymer processing aid, like a fluoropolymer type, could be used to reduce the melt fracture and therefore reduce the buildup of the die. That's one thing. If now we have a problem with the volatile, we have to identify, is the melt temperature too high? Do we have too much shear heating? Because those BOPP processes are huge outputs, and I've seen very, very high very high rates. We're talking about 5 tons or even, let me think about it. Yeah, it's like a 1.2 meter die and it's over 6 tons an hour. Huge output. So a lot of shear through the system could be the issue. So maybe some ways to lower the viscosity of the melt, looking at a little bit slightly higher MFR. I know they use copolymers and terpolymers for the skin layers. Those also, I would have to compare with the traditional homopolymers if they could potentially result in more melt fracture. I don't think so, but so whoever asked the question, I'd be willing to work with them, because that's I think that's an interesting one, and I like BOPP too. So
next question: if a capillary rheometer shows negative slope, bad fitting to the correction, can you suggest how to deal with the situation?
I'm not sure what slope they're talking about. Negative slope of what? I'm not sure.
Okay, if you want to, whoever submitted, if you want to resubmit with an update.
Yeah.
Next, do you have example of shear behavior of polymer with high loads of minerals as carbon black, for example?
Carbon black, maybe not, but I do have a lot of highly loaded polymers out there. Yes, and quite interesting behaviors. I don't know. I don't think I have time to pull anything here. I don't have one in the presentation. So same thing, whoever asked that question, I will be happy to answer separate.
Do you consider wall slip on die flow simulations?
Typically not, but and the reason is that, characterizing the slip, as I mentioned, the Mooney method, similarly to Bagley or the historical Bagley, you have to use many different dies, and it's more like a research project. We have ways to deal with that without saying too much. That we know how to correct from it versus actually modeling the slip in the flow simulations.
Okay. What is the best point to modify rheology? Changing the temperature in the extruder or in the die?
To modify the rheology, you have many ways, but the impact of die temperature is usually fairly low because of relatively short residence time, typically, and the polymer, thermal conductivity being fairly low. There's not enough flow length or time for the material to be either cooled or heated up. There's some slight impact, but it's not typically enough, right? And setting melt temperature is definitely a more efficient way.
Next, what are some practical ways extrusion manufacturers using capillary rheometry as an incoming material check? And have you seen data used to maximize process performance?
This is what we do all the time, right? So we try to optimize processes through these measurements. I'm not sure what else I could say.
That's fine. As a material's PVT heat capacity and thermal conductivity characterized and employed in the simulation, are these properties significant to the extrusion processing?
The PVT?
Yeah, PVT heat capacity and thermal conductivity.
Well, heat capacity, thermal conductivity are definitely part of the flow simulations, because one thing I didn't mention because of time is that all the models I present are actually non-isothermal, meaning that the flow will generate some heat from the high viscosity, so almost like friction, right? That's what viscous dissipation is, and that heat will travel different ways and will be either transferred to the wall through conduction, will travel with the flow, and that's convection. And so, yes, these parameters are the thermal parameters, conductivity, heat capacity, and density are all used in those simulations. Now, the PVT is not used for extrusion much. The reason is that most of the flow is under pressure, and so if you know the melt density at that pressure, that's basically what you're going to use for the model. Now, it's in PVT information is very critical for injection molding, for example, where we have quite a bit of changes through the pressures during injection, the packing phase, and the cooling phase. And the temperature is also, the range of temperature is also huge. Here in extrusion, the die is supposed to match the melt temperature, more or less, right? So we have some temperature variation in the process which are minimal compared to injection molding, where we inject a really hot melt into a cold mold. And at the end, the physical properties and the part dimensions are depending on those PVT diagrams. So critical in injection molding, not so much for the flow inside the die or inside the screw or so on and so forth in extrusion.
Okay, next question. How do you do time sweep in capillary rheometer? Doesn't material leave instrument during the test?
So we load the material in a barrel, we melt it, and then we would basically do a normal test, but we make a very long, we basically block the test to one shear rate. So for example, I will take a shear rate of 20 and the piston is moving slowly. The material is flowing through the die and the pressure is measured over time. And so it could be over an hour, for example. Yeah, that's how we do it. Very simple.
Okay. Why are 2 deviations used in calculating the variance instead of 1 or 3?
Oh, I use the standard from the gauging people. I don't know why they use 2 sigma, but that's industry standard. So I use the same 2 in my result of the velocity profile to kind of compare with the gauging people. So that's why I use it.
Okay. How would you evaluate process aid performance with a rheometer?
Well, you could try different compounds, different concentrations, and if you experience, well, it depends on your goal in the end, but if you're, for example, experiencing melt fracture, you could try to detect where the critical shear rate will be and if there's any influence of the composition. And for example, higher concentration of PPA, higher critical shear rate or something like that. You can look at, compare the thermal stability, you can compare the overall viscosity versus shear rate. So there's a bunch of stuff you could do. But that's those 3 things is basically what I would try.
Okay, next question. Target die-lit variation. One slide had a variation of 16% and gave non-uniform sheet thickness. Do you recommend a specific value to target during design? 5%, 10%?
We design for 0% deviation. I know it sounds crazy, but so when we design, we actually have a numerical optimization to reach 0% in theory. Of course, then most customers will have more than one formulation or one film structure. So we're going to look at all these different film structures. We want to sort of rank them through priorities and look at all these. And there's different design strategies on depending on those strategies. And sometimes we have to compromise things. But in general, to answer the question, I would think that a plus minus 10% variation is, let's say, acceptable. Beyond that, we kind of raise the flag and would like to stay within that range, right? The lip can correct those plus minus 10%, depending if it's automatic or if it's manual. But yeah, beyond that is a little more questionable, let's say.
Okay. Can we compare capillary rheology with the Rheology Online executed with a micro-rheology compounder with slit and rod die capillary modules?
You can do whatever you want. Yes, you can compare. I think I'm surprised I didn't have the question yet. Which one is your favorite technique? Is usually the one that comes up. And my answer is like, well, first of all, what do you have in your lab? Go ahead and use it. And I think that the techniques are all giving you information that is interesting. So capillary is a critical for extrusion, but so is rotational. And so if you have a micro compounder and you can do measurements with a slit die there, that's great. I would definitely do it. Now, the thing is, there are limitations as well. And one of them can be that you're not able to cover a range of shear rate that makes sense for what you're looking at, right? The good thing with capillary is that it really matches what we are dealing with in extrusion or injection molding. And one quality I like with the rotational is we can cover slightly lower rates and get maybe more precisely more precise data at low rates and get a better Newtonian plateau resolution there. But then the issue is that we can't cover the higher shear rate range as well. So there's different ways to deal with that. One being applying time temperature superposition and covering a whole range of frequencies with basically doing measurements at different temperatures. Now with direct extrusion measurements, usually one issue is you have a fairly narrow coverage of shear rates. And so that may not completely show what's going on in the Newtonian region, and that could be actually a critical portion of the flow that you're looking at. I don't know what this person is trying to do, but that there are limitations for every technique, but there's also some strong points. So personally, I do not have any type of online measurement, but I would love to. But that way I would cover pretty much all the techniques.
That takes us to the end of our questions. Thank you, Olivier, for an enlightening presentation. Do you have any final comments?
No, I really enjoyed it. And so maybe the next one could be on co-extrusion. Let's see.
Great.
So any comments or suggestions from the attendees today would be also welcome.
Okay.
Thank you.
We will be posting the presentation and recording in the SPE library, and you also receive an email with a direct link. Please be sure to check out our upcoming webinars and have a fantastic day.
Thank you very much again.